Okay, so welcome to our second Israel Algorithmic Game Theory seminar. Today's speaker is Yannai Gonczarowski, and he'll talk about Bulow-Klemperer result for two-sided markets. So welcome, Yannai.
Thanks so much for having me here, and thanks for organizing this this great seminar. I think if there is a silver lining to what's going on now, it's these unified seminars. Okay, so let's start. So this is joint work with Moshe Babayo from Microsoft Research in Herzliya and with Kira Goldner at Columbia. And I'm going to tell you about Bulow-Klemperer-Style results for welfare maximization in two-sided markets. So let's start with two-sided markets and then work our way toward Bulow-Klemperer. So here's the model. It's a quite standard model, many times referred to as a double auction setting. We have MS sellers, so a finite arbitrary number of sellers. Each of them holds one item. All the items are identical. We have an arbitrary finite number of buyers, MB, potential buyers, I should say. Each of them is interested in any one item. Each seller J has private cost Sj, non-negative, for parting with her item. Each buyer I has private value Bi for obtaining an item. And a trade is a specification of which sellers are going to part with their item and which buyers are going to be obtaining these items. These sets should be of the same size. And the trade is efficient if it maximizes the gains from trade, the sum of values of the buyers that get items minus the sum of costs of the sellers that part with their items. And the ideal goal in this setting is to find a mechanism that is a function from all of the values and costs, telling you if these are the values and these of the buyers and these are the costs of the sellers, then here's the trade. And here are payments or charges for each participant. Usually we're going to have payment toward buyers and charges from sellers. And we want this mechanism to satisfy certain properties. First of all, individual rationality, allow voluntary participation. By this, we mean that the utility of any participant is always going to be non-negative. The utility is the value or the cost for the outcome, value for the outcome if it's a buyer, cost for the outcome if it's a seller, minus how much this buyer is charged or plus how much the seller is paid. So it's a number and it should always be non-negative, it should always be non-negative. Zero means the utility when you don't participate, you don't pay anything, you don't get anything, or don't part with anything. It should be incentive compatible, meaning that it should incentivize truthful reporting. Your utility should always be highest when you're telling the truth, when you're reporting your actual value or cost. It should be weakly budget balanced, meaning that the mechanism does not lose money. We don't mind if the mechanism makes money, but the mechanism should not lose money. You can think about this as individually rational for the auctioneer. And finally, beyond these feasibility constraints, we wish for it to be efficient, meaning that for any profile of costs or values, it outputs a trade that is efficient, a trade that maximizes the gains from trade. So VCG is one great mechanism that we all love very much. It's a very generally applicable mechanism. It's individually rational, incentive compatible, efficient. So you may wonder, why is this talk even taking place? Just use VCG and that's it. VCG, for whoever needs a short reminder, is a mechanism that simply outputs the efficient trade, charges each trading buyer her minimal trading bid, and pays each seller her maximum trading bid. So let's look at an example. If there's one buyer with value 10 and one seller with cost 9, it's obviously efficient to trade the item. You get gains from trade of 1. There's an overall welfare of 9 if you don't trade and 10 if you do. Buyer's minimum trading bid is 9, right? If the buyer says 9 or more, then it's efficient to trade, so the buyer pays 9. The seller's minimum trading bid is 10, because if the seller says 10 or less, it's going to trade, so the seller is paid 10. And VCG runs a deficit of 1 because it has to get 9 from the buyer and somehow pay 10 to the seller. So VCG is not budget balanced, and that's the problem with using VCG in this setting. And more generally, there's a beautiful impossibility result by Myerson and Satterthwaite saying that not even VCG, regardless of the mechanism that you use, even for one seller and one buyer, there is no mechanism that is simultaneously individually rational, incentive compatible, budget balanced, and efficient. So when I say ideal, when I said an ideal goal in the previous slide, it really is the ideal unattainable goal. So what can we do here? So the first best efficiency, what's called the being efficient for every profile, is infeasible. So one way to proceed is a Bayesian setting. A go-to mechanism design approach is to maintain the feasibility constraints and somehow relax efficiency. In a Bayesian setting, this would be assuming that the values and costs are independently drawn from some distribution. Find a feasible mechanism with optimal expected efficiency in expectation over this distribution. This is what's called the second best mechanism. It need not be efficient for every given input, but in expectation, it's the best you can do without giving up on the 3 feasibility constraints, IR, IC, and budget balanced. The downside of this is that we know that the second best mechanism needs to be carefully tailored to the Bayesian prior, and it's known to be extremely complex when we understand it, and actually eludes a precise description in the very general case for any distribution. And this showcases that, as in many other mechanism design settings, an inherent trade-off between efficiency on the one hand, and on the other hand, the simplicity of the mechanism and the amount of knowledge required by the mechanism. As I said, it has to be very carefully tailored to the Bayesian prior if you're taking this approach. So we're not going to take this approach in this talk, but rather an approach that is inspired by another line of work in the one-sided market literature. So here's a canonical setting, a one-sided setting. There's one seller with one item, M buyers, any number of buyers, each of them with a drawn private value drawn from some distribution. And the goal is to maximize the seller's expected revenue. And the go-to approach here, very similarly, is to find an IR and IC mechanism. Here you don't care about budget balance. It's not constrained because the seller does not have any cost to part with the item. It maximizes the seller's expected revenue given the buyer value distributions. And here the optimal mechanism, very similarly, even for I.D. bidders, requires information about the distributions and has similar problems. And Bulow and Klemperer in 1996 gave a beautiful, different approach to deal with this problem. They said with I.D. bidders, under certain assumptions on the distribution, we'll get to that later, if we can recruit one more similar buyer, that is, one more buyer sampled IID from the same distribution. If you originally had 11 buyers, now you will have 12. If you originally had 1 million, now you'll have 1,000,001. Then we can beat the trade-off from the previous slide, this trade-off between efficiency on one hand and simplicity knowledge on the other hand. There exists actually a simple, prior independent, meaning that it doesn't need to know anything about the distribution, feasible, in this case, IR and IC mechanism that in the augmented market, the one with 1,000,001 buyers, gives expected revenue at least as high as the optimal revenue of the first best in the original market. Or in this case, sorry, of the optimal revenue of the second best in the original market. And this is quite remarkable. You add just one more buyer, regardless of how many buyers you had to begin with, and you completely beat the trade-off. You get the best of all worlds. And we're in this talk going to
Yannai,
yeah.
something.
Yes.
You switch from efficiency to maximize revenue, which is not
I know. I did not switch. This is the one-sided.
No, you want to approximate problems of maximizing of efficiency, and now you are now talking about things with maximal revenue. Just noticing it. That's all.
You're right. And as I said, we're taking inspiration from this line of work. We're not going to translate it one for one. And this is the almost last thing I'm going to say about this line of work. It's just contextualizing our results. So today I'm going to tell you about Bulow-Klemperer-Style results for two-sided markets. So it's going to have the same flavor of beat the trade-off. So I'm going to tell you about a simple, again, prior independent. You don't need to know anything about distributions. Feasible, you're going to have budget balance as well here. Mechanism that in an augmented market gives expected efficiency. So we're back to efficiency, Sergio.
Yes, I should have waited for one more bullet before asking. Yes.
Yeah, that's a recurring theme. Sorry. That's at least as high as the optimal efficiency in the original market. So our first main result is quite easy to phrase. We have, as I said, MS sellers, MB buyers, values and cost for now. This is going to change later. Will be drawn IID from some distribution F, arbitrary, doesn't need to be regular or anything. And the augmented market here is going to have one more buyer with value independently drawn from F. So the augmented market is going to have MS sellers, MB plus one buyers. Even if MB is a million or a zillion, you just add one. And the theorem, this is informal, we'll say it formally in a few slides. There exists a mechanism, we'll talk about it soon, that is simple, prior independent, meaning that it doesn't need to know what F is. Individually rational, incentive compatible, budget balance, so other feasibility constraints, so that this mechanism in the augmented market has expected gains from trade, at least as high as the optimal yet infeasible VCG market in the original market. I remind you that VCG is the first best. Having gains from trade at least as high as VCG is exactly the same as having expected welfare, having efficiency at least as high as VCG in the original market. So you add one more and you beat the trade-off. I'm talking about adding a buyer here, but the same also holds if you add a seller rather than a buyer, then it's a slightly tweaked mechanism, but it's as simple. The full details are in the paper. We have an aesthetic preference to phrasing things in terms of adding a buyer because it has the same pre-trade welfare. It doesn't seem like you cheated by adding items to the market, even though when you talk about gains, it doesn't really matter. And the same thing about holding, even if you add a seller or sellers rather than a buyer or buyers, will hold for any other result that I'm going to talk about today as well. So you're probably wondering at this time, what is this simple mechanism? So let's talk about it, and let's start with a simpler case of describing this mechanism for only one seller. So any amount of buyers, one seller will generalize to several sellers soon. So what you would have wanted is a second price auction with the seller's cost as the reserve, right? Because that's efficient. It trades if and only if someone values the item by more than the seller. And it's budget balanced, obviously, because people will pay more than how much you need to pay the seller. Problem is that it's not incentive compatible for the seller. The seller many times may have an incentive to overbid their cost to also get some revenue. And so second try here would have been, and this is actually what we're doing, second price auction with seller veto. Takes a while to think about and understand why it's right, but it's a very simple mechanism actually. First, among the buyers, you run a second price auction with no reserve. So the highest value buyer wins and pays the second highest value. And next, the seller has a choice: either accept the result of the second price auction, which means that the seller is going to get paid the second highest buyer value for her item, or veto it if this price is lower than the seller's cost, resulting in no trade. So unlike the second price with seller's cost as a reserve, this is incentive compatible because the seller cannot bid anything different to get paid higher. The seller can only say, I accept this price or I reject it, and then there's no trade, but it's not efficient. For example, there's no trade if the highest, it's not an example actually, it's the only bad case. There is no trade if the highest buyer value is higher than the seller's cost, which is in turn higher than the second highest value, because then it would be efficient to trade because there is some gains to be made here. but the second highest value, which is what the seller gets as a price offer, is lower than the seller's cost, so the seller is going to decline. Nonetheless, we're going to show that the efficiency in the augmented market is greater than the optimal efficiency, the first best efficiency in the original market. Equivalently, that the gains from trade in the augmented market are going to be greater than the gains from trade in the original market. And let's now talk about how to generalize this description for more than one seller. So I'm going to describe to you now the completely general mechanism, but for one seller, it's going to reduce to this eventually. So we call this mechanism buyer trade reduction, BTR. It's very much inspired by McAfee's classic trade reduction mechanism. There's a slight tweak, I'll show it to you. And here's the description of BTR. So you start by sorting the reported buyer values. So this is going to be instead of compatible. So reported buyer values, we're going to assume that they are the actual buyer values. So I'm not going to make this distinction anymore. You sort the buyer values in decreasing order and the seller costs in increasing order. So something like this, you see these are decreasing from the buyer that the mechanism likes least, and from the seller that's best for the mechanism till the least preferable one. And then you calculate the efficient trade size Q. How do you do this? You note that until this line, buyers are greater than sellers, so you want to trade because there are gains to be made. Beneath this line, buyers are less than sellers, so no gains to be made here. So this is the efficient trade size in this case, and this is the efficient trade. These two sellers keep their items. These three sellers switch their items to these three buyers. This is the first best. This is the most efficient thing you can do. Obviously, there are degrees of freedom. Doesn't really matter if the item of the 45 goes to the 90, to the 70, or to the 60, but we're going to think about this specifically as the best trade. And the first thing you attempt to do is to trade at the value of buyer Q plus 1 at the price. So in this specific case, set a price of 50 and check if all these trading sellers and buyers take that price. In this specific case, they do. All of the sellers have cost less than 50. All of the buyers have values higher than 50. That's awesome. That's great. In this case, you would get full efficiency. But what happens if this is not the case? So for example, what happens if this losing buyer has a value of 40 rather than 50. In this case, if you try to trade at this price, this seller is going to say, sorry, 40 is too low for me. So if a trading seller has higher cost than this price, then you reduce the trade between seller Q and buyer Q. So you do not perform this trade. And you trade the top Q minus 1 pairs. So it's inefficient, but you drop the lower one. You only trade these pairs with all buyers paying the value of the reduced buyer. So in this case, 60. And with all sellers getting paid the cost of the reduced seller. So in this case, 45. And this is always fine because the reduced buyer is less than all remaining buyers, and the reduced seller is more than all remaining sellers. So this is always fine. And this is the mechanism, and it turns out to be prior independent. As you saw, I did not have anything here depend on any underlying distribution. It's individually rational. As we constructed the payments, no seller is ever going to be paid less than their cost. No buyer is ever going to pay more than their value. It turns out to be instead of compatible. I'm not going to check this. This is very similar to McAfee's proof for the trade reduction mechanism. And it's budget balanced. As you saw, the mechanism never loses money. Either everyone trades at the same price or the buyers pay more than the sellers have to be paid. And I should note that the main tweak here is in the fact that the value that we attempt to trade at first is the value of buyer Q plus 1. And the second main tweak is that we reduce and trade anyway and not, and the way that we exactly do that. Okay, so first main result, formal restatement. This is a restatement of what we said before. For any number of sellers, any number of buyers, any distribution F, the expected gains from trade from BTR this mechanism in the augmented market is at least as high as the expected gains from trade of the first best mechanism of VCG in the original market. And I'm stating it here in terms of gains from trade, but you could have said expected welfare and expected welfare, expected efficiency would have been exactly the same. So here it doesn't really matter. This interpretation will matter later. Questions so far? I think this is a good time to jump in if anyone has.
Yes, I have a question.
Yeah.
Where is the additional buyer?
Where's the additional buyer? You'll have to help me out here. This mechanism.
Augmented.
Okay, so
you had a buyer.
Yeah. Okay, so this mechanism is this the description for a mechanism in a market? You can run it for 1 million or 1,000,001 or 1,000,005 buyers. So this is just a description of a mechanism. In this theorem, it says BTR in the augmented market. You see that BTR with MS sellers and MB+1 buyers gets higher expected efficiency or gains from trade or whatever than opt with MS and MB buyers. So the fact that the market is augmented is in the fact that you let BTR get one more buyer than you let opt have. Okay, so the mechanism is just a description of a mechanism. It doesn't care about augmentation. The statement of the result says if you give one more buyer, then this performs better than this does if you don't give it one more buyer. Okay.
I have questions.
Yeah.
You have a symmetry between buyers and sellers, but you choose at the beginning the price, the Q+1 of the price.
Yeah. Good. So if you want to add sellers, and remember that I told you that you can also add sellers instead of buyers, and you're going to have a slight tweak. That's a tweak. You're going to trade at the seller instead of at the buyer, and etc.
Mm-hmm.
So that's, yeah, you do the opposite thing if you want to add sellers.
Mm-hmm. And one more remark, I mean, this type of mechanism is used in the past a lot with the stock market, I guess. I mean, probably other places as well, but for some reason they stopped using it, maybe 10 years ago or so.
In the stock market?
In the stock market, yeah.
I'm not familiar enough with that to give you a...
I mean, they moved from multiple buyers and sellers to two-sided, one-on-one for some reason, and they stopped using this mechanism. Maybe 10 years ago or something like that.
Okay, I'm not familiar with that specific thing. Moshe, do you have anything to say about that?
No, I'm not sure. Which stock market are you talking about?
For example, the Israeli one, but also the Nasdaq and whatever. I mean,
throughout the day, it's a continuous mechanism, right? This is kind of like an offline mechanism. It's not a continuous time mechanism.
You're talking about the order book, right?
Yeah.
That's called order book, and that's essentially what they do. Now, exactly what price they do, that probably has changed, but they exactly look at the order book, order buyers, order sellers, and see where you put the cutoff and so on. Question is exactly how you decide what you decide at the cutoff, and that may change.
But I think that in the stock market, you never leave an efficient trade on the table. So, if there is one buyer that is willing to pay a price and the seller is willing to accept it, the only question is which price they will trade, but there is always this trade will happen, right?
Yeah, here we reduce a trade that could have happened, and we reduce it in the interest of incentive compatibility.
Mm-hmm.
Okay, great. So let's move on. So notice that once again that this result does not need any kind of regularity, and we're going to use the term robust from now on for prior, independent, and feasible. Okay, so what happens with more than one buyer, or what happens with non-I.D? What happens if the buyers and the sellers, for example, are drawn from a different distribution? So if these distributions are unrestricted, we have a very strong negative result for augmenting actually the market with any number of sellers and or buyers, and for any mechanism, not necessarily BTR. So let M be any anonymous, robust, deterministic mechanism. So robust means prior, independent, and feasible. Anonymous means, roughly speaking, equal treatment of equals up to tie breaking. So if you're going to permute the values and permute the cost, it means that the critical values get permuted the same, or actually the only thing that we need here is that if there is no trade before permuting, then there is no trade after permuting. So it's a really, we're not hiding anything here.
Sorry, Yannai, just a clarification. Previously, you had just one F. That was for buyers, for sellers, for both?
Yeah, so we had one F for both buyers and sellers.
Oh, so the costs and the values of the buyers were the same distribution. Oh, I didn't notice that. Okay, that's important because usually that's a very strong assumption.
I know, and that's where we're.
Okay, no, I didn't notice that. Okay.
Yeah,
I didn't notice that. I'm just now that you have two distributions, I suddenly understood.
Yeah, okay. So that's why the previous section was.
So now you have only two. Now all the buyers are symmetric.
Yeah.
And all the sellers
now,
are symmetric?
now all the buyers are symmetric and all the sellers are symmetric. In some sense, you can't really hope for much more than that because you need to have meaning for recruiting a similar buyer, right? If every buyer is drawn from something different, also Bulow-Klemperer breaks.
No, but that's a negative result anyway. So just
I know, but
strengthens your result.
Yeah, but the talk is not going to end here. We're going to have positive results for different distributions.
Okay, but I actually wanted to ask. Okay, go ahead, Sergio.
I just said he has a positive talk. You don't want him to end on a negative. Sorry.
Can you explain again the significance of anonymous? I didn't follow what you mean by anonymous.
So anonymous here, I mean that if there is no trade, like here's the least thing I need to require. If there's no trade at some profile of values and costs, if you permute the costs and values among the sellers and the values among the buyers, then there will still be no trade.
Okay.
Yeah, so let me continue with it. Are you also talking about randomized mechanisms?
No, I'm not. That's where I'm actually hiding something. I was wondering whether anyone would notice that. No, so here we're only talking about deterministic mechanisms. That is the limitation. Yeah.
And I have a question.
Yeah.
Maybe you can give some intuition as to where you, in the positive result, where you use the identical distribution.
I'm gonna give you the full proof of the positive result at the end of this talk.
Okay, thanks.
Okay, thanks. I didn't see who asked this, by the way, due to Zoom.
Me, Ben.
Oh, okay, thanks. Okay, so what's the negative result? Let M be any anonymous, robust, deterministic mechanism. For any epsilon, so epsilon is going to mean that this mechanism, whatever you do, is going to get less than epsilon times the optimal. For any number of sellers in the original market, for any number of buyers in the original market, for any number of sellers that you add to create the augmented market, for any number of buyers that you're going to add to create the augmented market, there exist two distributions, Fs and Fb, such that this mechanism in the augmented market doesn't even get an epsilon fraction of the gains from trade of opt in the original market.
Question.
Yeah.
And how does anonymity pertain to comparing a mechanism for, say, ms equals 2 and mb equals 7 to a mechanism for ms equals 7 and mb equals 10?
No, so all you need here, here M is a mechanism for ms plus L sellers and MB plus K buyers. M can
so
be
any connection between mechanisms for different sizes.
No connection whatsoever. There's no restriction. Here, all you need is that if you keep MS plus L sellers but permute their costs and keep MB plus K buyers but permute their costs, if there was no trade, there still is no trade. That's the restriction here. So we don't do anything fishy of that kind. We don't compare different games or stuff like that, like other axiomatic approaches in different parts of game.
So in short, for all MS and B can and for all LK can come at the beginning of the sentence.
That's true. That's true.
And then I would not have asked the question.
Okay, fair enough. Fair enough. Okay.
Sorry,
fair
John,
enough.
sorry.
No, that's a good comment. Thanks. Okay, so and actually we don't only show this compared to the first best, we also show this compared to the second best. So even if you're fine with feasible op, the mechanism that gets you highest expected gains from trade given efficiency, still the same thing holds. So it's not that this is the wrong benchmark or too strong a benchmark. And the intuition here is that if any, much like in Bulow-Klemperer's original result, if any buyer, single buyer, is rarely above the seller value, but when it is, there are lots of gains from trade to be made, then there's super slim probability of another buyer also being above that seller value, and that's what's needed for BTR not to reduce the trade. This is exactly the same thing that kills Bulow-Klemperer without their assumptions. And for this reason, for the rest of this talk, we're going to assume that FB first order stochastically dominates FS to avoid these cases. And this should be compared with Bulow-Klemperer's assumption of serious bidders. So you all know that Bulow-Klemperer requires regularity. We're actually not going to require that. But another assumption of Bulow-Klemperer is that the support of the buyer distribution be so that the minimum of that support is higher than the seller's cost. And
so
actually,
the problem, yeah, sorry.
Let me just finish this sentence. And FB, first order stochastically dominating FS, is actually a generalization of saying the support of FB is higher than the support of FS. Yes.
So the problematic cases are when the optimum is in fact extremely small relative to the size of the market, because there is those are the counter examples. So the question is, can you deal with things where there is a positive gain relative to where the optimal mechanism gives you a constant times the size of the market.
You need to be careful here, because everything you said everything you just said right now is not very robust to change of currency when you say small or big compared to the size of the market.
Well, the number of people that make trade is small o of the size of the market. That's
okay. That's yeah.
And what I want is not to be small o, but to be constant. So
the problem always is when only very few pairs trade.
Yeah.
But yeah, our results are going to be completely general, and even for such cases. What we need is stochastic dominance to avoid these hopeless cases, but that's it, and we'll talk about that soon. So let's continue.
Well, stochastic dominance is strong. I wanted something weaker than that, but okay, never mind.
Okay, it's weaker than last week's assumption. So maybe next week you'll have an assumption that you like. Okay, let's continue. Sorry about that. Okay, so let's talk about one seller and one buyer. So here we start by having a qualitative miss. Even with stochastic dominance, any anonymous robust deterministic mechanism, there exists two distributions Fs and Fb, such that Fb first order stochastically dominates Fs, such that if you add one buyer, it's not enough. So this is for any deterministic mechanism, not only for ours, but we still want to get a qualitative hit. And this is even for the second best. Can we get a qualitative hit? Can we have a recovered theorem that says if FB first order stochastically dominates Fs, then okay, you can't add one, but you can add some numbers. And here, it's surely adding 10 suffices, but the question really is how much can you add, right? Or let me rephrase, surely adding 1,000,000 should suffice, but we really want to get some better number. Or maybe surely adding 2 to the 100 should suffice.
And the question if that number depends on F, of course.
Okay, so the question is,
there is a number.
Sergio, please wait. Whenever you want to ask something, wait one slide, see if it gets answered, then.
So Yannai, from your intonation, it seems that the answer is no.
So here's, before we continue, let's take actually a short poll. Let's use Zoom, and each of you guess the result. How many buyers does it suffice to add with stochastic dominance to beat the gains from trade or the expected efficiency of the original number of the original market?
What?
You have to choose your guess. This is the.
Wait, now For every
Okay, are we done? Okay, so you guys are pretty pessimistic. Let me make you a little bit more pessimistic before we continue. So let's how do you get intuition for this? So let's take a short aside, and you'll see soon why this is important. And let's talk about sample pricing. So a celebrated result of Bulow and corollary of Bulow-Klemperer due to Dhangwatnotai et al. 2010 is that in a revenue maximization setting with one seller and one buyer, with values distributed according to BK's assumption, if the seller can get one fresh independent sample from the buyer's distribution, then pricing the item at that sample gives an expectation at least 1/2 of the optimal revenue. So all you need is one sample, you price at that, you get 1/2 of the optimal. That's quite surprising that one sample has so much information in it. And we use a similar reduction, even though our proof of our BK result is very different from BK's original proof. This reduction is actually quite similar. And we give the first result that we know of for sample pricing in two-sided markets that says for I.D., for one buyer and one seller with values drawn I.D. from the same distribution, pricing at a single fresh independent sample, meaning that we get one additional sample from F, and pricing at it means that there is going to be trade only if both the seller and the buyer agree that this is how much the buyer is going to pay the seller. Obtains expected gains from trade at least 1/2 of the optimal. This is without adding buyers or sellers, but you do need access to a fresh sample, fresh independent sample. This is, I should note, till now, I always said beating the expected welfare in the original market is the same as beating the expected gains from trade. When you talk about fractions, beating the 1/2 of the expected gains from trade is actually stronger than beating 1/2 of the expected optimal welfare. So this is the harder thing you could think of. We also show that nothing better than 1/2 of opt could be guaranteed. For many distributions, what you get is exactly 1/2 of opt. So this is nice. And this is, you can ask, what about non-IID? Because I promise you that you're going to learn something from this, for this aside for the question that I asked you about. What about FB that first order stochastically dominates FS? So this is our IID result. And once again, we can't really replicate it for stochastic dominance, but here we can do something qualitative. We do get a qualitative hit, what I call for stochastic dominance. If for one buyer with value distributed according to FB and one seller according to FS, where there is stochastic dominance, pricing at a single fresh independent sample from FB obtains expected gains from trade at least 1/4 of the optimal, so it's qualitatively still a constant. We don't know to show that 1/4 is tight. We do know that to show that you can't get more than 7/16, and this number is crucially important because it means that you can't get 1/2. So there is really a separation here between IID and stochastic dominance. So you're probably still wondering what this has to do with the original result, that the original question that I asked you. So let's talk about some connection between sample pricing and adding buyers. So here is a lemma that we proved. It's going to look a bit bizarre, but let's take it in. So for any seller distribution FS and any buyer distribution FB, if it holds for a certain K that adding K buyers and running BTR beats the original market, so if this holds for 10 or a million or 2 to the 100 as before, then the following holds also for the same K. If this holds for adding 10 buyers, this would hold for a K equals 10. If this holds for adding 100 buyers, this holds for K equals 100. It is in a setting with one buyer and one seller, pricing at the maximum of K samples drawn IID from FB obtains expected gains from trade at least 1 over 1 plus k of opt in the original market. So I phrase it in terms of this implies this. If FB an atom is atomless, then these are actually equivalent. So think about these as being equivalent for many reasonable distributions. And recall that earlier I asked you, like, does this surely hold for some k? And since this implies this, then if this surely holds for some k, then this surely holds for the same k. But let's think about this. On the one hand, getting at least 1 over 1 plus k of opt is easier as k grows, right? For k 1,000, you only need to get 1 over 1,001 of opt. For k 1,000,000, you only need to get 1 over 1,000,001. So this seems to be easy as you add more and more buyers here. But on the other hand, pricing of the maximum of k samples drawn I.D. from FB for large k is completely absurd, right? If you're going to draw 1,000,000 samples from FB and price at that, what are the chances that the buyer whose value is a single sample from FB is going to be more than that, is going to agree to this, is going to agree to this? So, or what are the chances that the seller is going to agree to this, etc. So this seems like completely absurd. And it's not even clear here that this condition is monotone, right? Had I asked you, look at this weird condition. Say that it holds for 10, that pricing at a maximum of 10 samples gets you at least 1 over 11 of opt. Does this mean that for the same distribution, it holds that pricing at a maximum of 1,000,000 samples gets you at least 1 over 1,000,000? At the maximum, gets you at least 1 over 1,000,001 of opt? Given the equivalence between two, you know that adding more buyer just helped, and you can tell me that this higher k also helps here, but even this is not obvious. So there's a really weird implication here of this thing. So given this information that I just told you, let me ask you again, what do you think about how many buyers it suffices to add? So please vote again, even if you already voted. You don't need to vote the same. Okay, so let's end the polling. And as you see, okay, so still most of you are very pessimistic and some of you are optimistic. Okay, so let's go back to sample pricing after we have some intuition for this. And can we get a qualitative hit? Which number is enough? Answer is 4 buyers are enough. But I hope that this little exercise that we did now makes you appreciate that this is not as simple or trivial or as you may have thought had I shown you this immediately without that detour. So what we showed is that adding 4 buyers actually is enough for BTR in the augmented market to beat opt in the original market. Regardless of the distributions, can be not regular, etc. All you need is stochastic dominance.
So you just don't know about 2 or 3?
We don't know about 2 or 3. That's open. We don't know. We'll get to the open questions later, but basically all of the gaps that you see here are open. Yeah, we don't know about 2 or 3, but 4 is enough.
By the way, Reinhard Zelten has a paper whose title is 4 is few and 6 is many. So you have few.
Okay.
By Zelten's definition.
Okay, so this already appeared in Soda, but when we prepare the journal version, we'll we'll note this to the reviewers that it's a few, so it's great. Okay, so what about many buyers? So we're now still one seller, but have many buyers instead of one. Do 4 extra buyers still suffice? Maybe some other constant. So in this case, we do have a more negative result. Let M be again any anonymous robust deterministic mechanism. And how do you read this? We're going to have stochastic dominance. So for any number of buyers k that you would imagine may suffice to add, there exists a number big N such that if you have more buyers than big N, there exists 2 distributions, FB and FS, with stochastic dominance such that adding k does not suffice. So again, as Sergio said, M can be here after the quantifiers, that's the same. So basically, if you tell me 1 million should suffice, there is a large enough number of buyers such that adding 1 million does not guarantee beating the original market for any 2 distributions satisfying stochastic dominance. So as the market grows, it becomes harder. You need to add more buyers. We do show, however, on the positive side, as usual, we also show this for the second best. We do show, however, on the positive side, that there is a number of buyers that you can add that depends on the initial number of buyers. So if you have MB buyers to begin with, if you add at least 4 square root of MB buyers, then you're fine. But crucially, as we showed here, you can't add a constant. You need to add something that depends on MB. We actually have a tighter lower bound. You'll see it soon. So this may seem like as there are more buyers, it's more challenging to beat opt. You need more buyers. So it may seem like with more and more buyers, BTR deteriorates. But curiously, this is not the case. Actually, we show that even without augmenting the market, in the original market, as you have more and more buyers, even if you take the worst case ratio between BTR and opt over any pair of distributions with stochastic dominance, as the number of buyers reaches infinity, you actually get 1. You converge to opt. So it's not that BTR deteriorates, but rather it is that as the market is very large to begin with, each extra buyer gets you less. So you need, even though BTR gets closer and closer to opt, you need more and more buyers to bridge this tiny gap. Right, and this should not surprise you that with a very, very large market, BTR converges to opt. This is, again, very much the same story as Bulow-Klemperer, or with many, many, many buyers, you're very close to opt anyway, right? The reserve price plays a less and less significant role as you have more and more buyers even there. So in both of these papers, really the largest gap between the simple mechanism that you introduce and opt is highest when the market is small, or where there's not a lot of trade in the market or something like that. Okay, so let's sum up the results before we move on to the proof. So 1 seller, 1 buyer, insufficient to add 0. That's by Myerson and Satterthwaite. No, their impossibility result shows us that no simple mechanism with desired properties can get us opt. But as we show, adding 1 suffices. That's the first result I showed you for I.D. We're going to see the proof in a moment. For any numbers of sellers and buyers, if you don't assume stochastic dominance, no finite number suffices. For 1 seller, 1 buyer with stochastic dominance, adding 1 does not suffice, adding 4 suffices. For 1 seller, any number of buyers, I told you that with stochastic dominance, I told you that adding 4 square root of MB buyers suffices. I told you that any constant number does not suffice. Actually, log number of buyers does not suffice. That's our lower bound here. And for many sellers and many buyers, this is the widest gap that's still open. Lower bound, we just carry over the lower bound from 1 seller. Constant or even log number of buyers does not suffice. And we show by a reduction to the 1 seller case that adding so many buyers, number of sellers times number of buyers plus 4 square root the number of buyers, this suffices. This is probably quite wasteful. And as I said, exactly the same bounds apply if you add sellers rather than buyers and use seller trade reduction rather than buyer trade reduction.
So Yannai, can I just say a comment?
Yeah.
So like the way I think about Bulow-Klemperer is that you have tons of buyers. You have many buyers and buyers. Yeah. And then the beauty of the result comes from the fact that you add a single buyer and you get this magic, right? Now here, if you look at single buyer and you need to add 4, you need to multiply the number of buyers in your market by 5.
That's true.
It's not like, so in a sense, it's less surprising that you can do something. Usually, like you think about it as a trade-off between improving your marketing, just to add 1 more or a few more, but multiplying the number, your market by 5.
So for a large market size, 4 times square root MB is much less than multiplying. Can I ask you, by the way, what did you vote in the previous poll?
I think you vouch for anonymous mechanisms.
I what? Sorry.
You wanted anonymous mechanisms in your theorem.
Okay.
So let's keep it anonymous.
Al is taking the fifths.
So anyway, a lot of people in the audience, which may or may not include you, still thought that 4 is surprising. So I see what you're saying about 4 not be surprising if you think about it in retrospect, maybe, but that's the purpose of those few slides in the polls.
So I take full responsibility about saying, mentioning the intonation, which might have caused the audience to vote this way or another.
Fair enough. Fair enough. So I agree. It's not as satisfying as it could have been. Still, BK. I agree that BK. It's beautiful that even with the large market you can add 1, but there's the strength of BK with the large market. You're super close to opt, as it is. So in some sense, the interesting case that gets you not a small fraction improvement, but a huge improvement is when you add 1 to 1. So it's true that here you need to add 4 to 1. But as I said, generally 4 square root of m, and more generally, this is 1 does not suffice. It's not a problem with our technique, and 1 does not suffice for any simple mechanism. I agree, it would have been cooler if 1 would have sufficed generally, but at least for I.D. it does. And you can think about, there are motivations for I.D. as well. Maybe buyers and sellers are ex ante the same, but some of them get items and then you want the market to equilibrate itself or whatever. So there are motivations for I.D. and then really the magic happens. You add 1 regardless of anything, and everything turns out nice.
Yannai, I just want to alert you that we have 5 more minutes.
I know.
Okay.
So let's. We have 1 more slide except for this. I'm not telling you how many lines are on that slide, but we have 1 more slide. So pricing at a sample, as I said, you take 1 sample. If everything is I.D., you guarantee 1/2, and that's tight. If with stochastic dominance, you guarantee 1/4, and you can't improve up to 1/2. This 4 and this 4 do not seem related, by the way. If anyone knows how to relate them, that would be great. Open, as I told Michal earlier, all the gaps here are open, so there's quite a lot of work to do here. And let me give you a 5-minute proof of the I.D. result. So we want to prove that BTR in the market plus 1 is greater than opt in the original market. We'll actually prove by comparing both of these to opt in the augmented market. So we're going to show that opt in the augmented market minus BTR in the augmented market is less than opt in the augmented market minus opt in the original market. And we're going to couple the original and augmented market as follows. We're first going to draw MS plus MB plus 1 values, so enough for the augmented market, IID from F. Let's sort them. And then we're going to uniformly at random choose MS of these to be sellers, MB of these to be old buyers, original buyers, and 1 of them to be the new buyer. And we're going to show for any realization of the first step in expectation over the second step that this inequality holds, that the expected optimal in the augmented market minus the expected BTR in the augmented market, expected is over the draws of stage 2, is less than expected opt in the augmented minus expected opt in the original. And I should note, even before realizing stage 2, once we've drawn these, we already know that for opt in the augmented market, the trading buyers and the non-trading sellers are going to be these guys. These guys are going to, in opt, are going to be the guys who keep the items, because that's the way to maximize welfare, right? For the MS top guys to keep to have items. So keep that in mind, that this is true even before we realize stage 2. And these obviously are the non-trading buyers, non-trading sellers. And let's reason about these two differences. So the first thing I'm going to ask for each of these differences is, when is it non-zero? So for this difference, I'm going to claim that it's non-zero if the new buyer is in the top MS values. Why? Because we know that the opt in the augmented market is the sum of the top MS values. We talked about that. These are the guys that keep the items. Opt in the original market is the top MS guys in the original markets. When do they differ? If the top MS guys in the original, in the augmented market, contain the new buyer. What's the probability of this happening? It's a probability of, so in stage 2, you choose the new buyer to be uniformly at random one of all of these guys. So it's MS, which is the number of top MS people, over the overall number of values, which is MS plus MB plus 1. The expected of the left hand, the thing you subtract from opt of aug, as we said, it's the sum of the top MS values in the augmented market. Sorry, this should be plus 1 here. And the thing that you subtract from it, opt in the original market, what is it? It's the top MS in the original market, meaning it's the top MS plus 1 values minus the new buyer that we know that it's in the top MS, so we have something to subtract here. So this expression basically is non-zero with this probability, and then it's this minus this. Let's look at this expression. When is it non-zero? I'm going to claim that it's non-zero if the MS plus first guy is a seller. So when did we say that BTR is not efficient? When it reduces a trade. When does it reduce a trade? When buyer, the value of buyer Q plus 1 is not acceptable to all the trading sellers and trading buyers. Specifically, buyer Q plus 1 is a non-trading buyer, so she's somewhere over here, like beyond this point. If she's the first, if she's value X MS plus 1, then she's acceptable to all the trading sellers who are in the, all Q first sellers who are in the right here, so we would not reduce the trade. If, though, the first guy who doesn't keep the item is a seller, then buyer Q is on the right here, and we will reduce the trade. So we reduce trade if this is seller. In fact, if this is seller Q, so that's the only case where this difference is non-zero. Probability for this is the probability that a single specific value here gets assigned to a seller and not to a buyer. We assign MS values to sellers, MS plus MB plus 1 to buyers. So again, same probability of MS over MS plus B plus 1, you get the point of this coupling. This, the thing you subtract from, is the same. Minus what? Minus the sum of the first, basically the efficient trade, but you keep seller Q, who's this seller, and you remove buyer Q, right? It's the optimal, except that you didn't get the gains from transferring the item from seller Q to buyer Q. So in each of these differences is non-zero with the same probability. You subtract from the same thing, and what you subtract is different. So in each of these, when you subtract, you get something minus MS plus 1, here and here. So what's this something? Here, it's the new buyer. What's the distribution of the new buyer condition on being in the top MS? It's a random value drawn uniformly from the top MS. this is buyer K. What's the distribution of buyer K? Buyer Q, sorry. Buyer Q, we know he's in the top MS. And it's actually, how do you draw buyer Q? You draw Q values. You draw Q buyers out of the first MS, and you take the minimum one. So here, this is a uniform value out of the top MS. Here, you draw Q values at random from the top MS, and you take the minimum of the Q. So this is smaller. QED, that's what we had to prove. These differences are non-zero with the same probability, and when they're non-zero, this is less than this. This is for every realization of stage 1 in expectation over stage 2. So it's also an expectation over both stages, meaning that in expectation over everything, left-hand side here is less than right-hand side here, meaning that what we subtract here is greater than what we subtracted here.
You only use exchangeability. You don't need IID, right? This whole proof is exchangeability. Mixtures of IID will work just as well.
Sorry, Sergio?
I'm saying your proof, if I understand it correctly, just uses exchangeability, not IID. You don't need mixtures of IID, for example, will satisfy that as well, because you are using step 2. You condition on step 1, and step 2 is exchangeability.
Yeah, good. Yeah. It could be that you first draw an IID.
You could have conditional IID. Yeah.
Yeah, you could have conditional IID. You first draw one of 10 IID distributions, then you draw every one of them.
Yeah.
You can do that as well.
Let's call exchangeability, which is even for finite, it's even more than that. But it's a small point, just.
For finite, I didn't get your last sentence.
For finite, for infinite, it's only mixtures of IIDs. For finite, more.
Yeah.
Exchangeability, it's a well-known condition, and that's what you should use.
Okay, thanks. So you're happier with this condition that you were before?
Yes, I'm less happy with the stochastic dominance, which is not. That's something I'm still. I understand that you need it, but I don't know. It's hard for me to see where it comes from.
As I said, also in BK they have actually a special case of that as their condition. You need something to.
No, I agree. Okay.
And I'm done. Thank you so much.
Thanks, Yannai. Thank you very much.